Hello everyone. Okay, so last class period was a big class period. We learned about the different types of IMFs and the different types of atoms that experience these IMFs. So if we look at the front of our packet here, we talked about the different types of IMFs. So reminder, those different types were London dispersion, dipole-dipole, and hydrogen bonding. Okay. And we also learned how to identify the types of IMF attractions between molecules. So if I have, let's say, we got this molecule. So if there's a sample of these molecules, the CF4 molecules, what are the intermolecular forces that occur between them? So the first thing you need to ask yourself is the molecule polar or nonpolar? So the molecule has 4 domains and all of those domains are identical, so it's a nonpolar molecule. So all molecules experience London dispersion, but only polar molecules experience dipole-dipole. So since this one is nonpolar, it only has London dispersion forces. Another molecule would be this O3 molecule. Here's the Lewis dot structure for that. Okay. So there are 3 domains around the center of this molecule. 2 of them are bonded oxygens, one's a lone pair. So not all the domains are the same. So because of that, we get asymmetry and it's a polar molecule. All molecules experience London dispersion, IMF attractions, and polar molecules like this one have dipole-dipole. There's a third type of intermolecular force, and that's hydrogen bonds. Hydrogen bonds occur when a molecule is polar, but then there also needs to be, within the polar molecule, a hydrogen that's bonded to either fluorine, oxygen, or nitrogen. So the really common one that we talk about with hydrogen bonding is water. So when I look at a water molecule, and let's draw the Lewis dot structure just so you can see it really quick. We know that of the IMFs that occur between these water molecules, it will have London dispersion because all molecules experience London dispersion. There's asymmetry. There's 4 domains, but 2 of them are lone pairs and 2 of them are bonded hydrogens. And that asymmetry makes it a polar molecule, so it experiences dipole-dipole. And then it has a hydrogen that's bonded to either a fluorine, an oxygen, or a nitrogen. And it's an oxygen, so this one experiences hydrogen bonding as well. All right. Relative strength. Okay, so strength of IMFs. Hydrogen bonding is the strongest. London dispersion is the weakest. So if I was looking at London dispersion, dipole-dipole, and hydrogen bonding, we are the strongest with hydrogen bonding, and we are the weakest with London dispersion. Okay. Next, we're going to talk about this relationship to boiling point. So in your packet, we're going to turn to page 15. Okay, so everyone, I want you to turn to page 15. Oh, and see on page 15, it discusses the strength again. So it's telling us that hydrogen bonding is the strongest IMF and dispersion, or London dispersion, is the weakest IMF. Right? Boiling point. The relationship between strength of IMF and boiling point is proportional. Okay? So let's write that down. So the relationship between boiling point and strength of IMF is proportional. Or let's do directly, is directly proportional. You know what directly proportional means. It means that when one is big, the other one's big, and when one is small, the other one's small. So if you see a really high boiling point, okay, so we have a big boiling point, that would mean that the strength of IMF had to have also been strong, or a big IMF. Or maybe you know that the IMF is weak, like it's only London dispersion. It only experiences London dispersion and it doesn't experience the other ones. And that would mean that it has a small boiling point. So let's review knowing the intra and intermolecular forces, and then we'll do some examples with boiling point. All right, when it's a water molecule, the types of atoms, so I see oxygen, which is a nonmetal, and hydrogen, which is a nonmetal. So if there's a water molecule, I'm going to draw it here. This bond, because it's two nonmetal, that's a covalent bond. So my intra is covalent. Now, if you have an electronegativity table, and I'll have those ready for you on the quiz, and then it's also in page 6 of your packet. And we looked at the electronegativity between oxygen and hydrogen. So we took this electronegativity of oxygen, 3.44, and we subtract it from hydrogen, 2.20. You get 1.24. And remember, that falls in the polar covalent range. Like if this difference, this subtraction of electronegativity, if it is less than 0.4, 0 to 0.4, we would say that it's a non-polar covalent bond. But that if it's greater than 0.4, then we're going to call it a polar covalent bond. And so this intramolecular force is a polar covalent bond. Now the whole molecule, is the whole molecule polar or non-polar? Let's check. 4 domains, 2 of them are lone pairs, 2 of them are bonded hydrogen. So that's asymmetry, so it's a polar molecule. Okay. So what are the IMFs it experiences? All molecules experience London dispersion. Polar molecules, like water, also have dipole-dipole. And then hydrogen bonding occurs when there's a hydrogen inside the molecule and it's bonded to fluorine, oxygen, or nitrogen. There is a hydrogen bonded to an oxygen, so we also get hydrogen bonding. So between water molecules, we experience all 3 IMFs. All right, next one. HCl, hydrogen and chlorine. So we get a nonmetal and a nonmetal. So this is what the Lewis dot structure looks like. Hydrogen, chlorine, and then there's lone pairs around the chlorine. Okay. This bond we know is covalent because it's 2 nonmetals. So then we can check to see if it's non-polar covalent or polar covalent with our electronegativities. The other thing you can kind of notice is chlorine has big electronegativity and hydrogen has small electronegativity. Like chlorine is 3.16 and hydrogen's 2.20. Okay. So 3.16 minus 2.2. 0.96 is that difference. So 0.96 falls in the polar covalent range. So this is in between, like that bond. Oh, sorry, I went too far. Right here. That bond inside is a polar covalent bond. Okay. Is this whole molecule polar or nonpolar? If chlorine is the center, we got 4 domains. 3 of them are lone pairs, and 1's a bonded hydrogen. They're not all the same. Asymmetry. This is a polar molecule. Okay. All molecules experience London dispersion as an IMF. Polar molecules like HCl have dipole-dipole. But HCl is not hydrogen bonding. And the reason why is because, yes, it does have a hydrogen, but it is not bonded to fluorine, oxygen, or nitrogen. So since hydrogen is not bonded to one of those 3, then in between this molecule and another molecule of HCl, it does not have hydrogen bonding. All right, we're going to skip NH3 for just a moment, and let's look at CH4. Carbon, nonmetal. Hydrogen, nonmetal. So it's another covalent bond. Okay, so it's another covalent bond. Oh, but is it polar covalent or non-polar covalent? So this is what the molecule looks like. And the bond is between carbon and hydrogen. So carbon has an electronegativity of 2.55. Hydrogen's 2.20. And if you subtract these, you get 0.35. So it is less than 0.4. So this bond, this intramolecular force, is a nonpolar covalent bond. Okay. Let's see if this molecule is polar or nonpolar. So we got 4 domains, and each domain is a bonded hydrogen. And that means it's symmetrical, so the molecule is nonpolar. Okay. Because it's nonpolar, all molecules experience London dispersion, but only dipole-dipole is when it's polar, and it's not hydrogen bonding either. So the IMF is only London dispersion. So between these 3 molecules, water, HCl, and CH4, the one that has the highest boiling point is water. This is the highest boiling point because it has the strongest IMFs. It has more IMFs and it has stronger IMFs. Then the next boiling point would be HCl because it's got 2 different types of IMFs, and this one is stronger than the London dispersion. And so for CH4, of these 3 examples, it would have the lowest boiling point. Okay. So let's practice that concept of boiling point. So let's turn the page. Sometimes I ask you for IMFs, and sometimes I ask for the strongest IMF. So let's practice an example where it's the strongest. So for each pair of molecules, think about the types of IMFs and predict which molecule in each pair would have the highest boiling point. I want you to think about the strongest type. So it may experience other IMFs, but we're just going to focus on the strongest one. Oh, and look, we've already talked about these ones. That was in the list before. So water experiences all 3: London dispersion, dipole-dipole, and hydrogen bonding. And of those, the strongest one is hydrogen bonding. Now HCl, it is a polar molecule, so it has London dispersion and dipole-dipole. So the strongest one was dipole-dipole. So what we're going to do is we're going to circle the molecule that has the higher boiling point. So higher boiling point, we're going to circle. They're directly proportional. So when the IMF is stronger, the boiling point is higher. Okay, number 2. Both of them experience London dispersion because they're molecules. I see asymmetry and then symmetry. So since NH3 is polar, it also has dipole-dipole. And then it experiences hydrogen bonding because a hydrogen is bonded either to fluorine, oxygen, or nitrogen. So it's polar and it has a hydrogen bonded to a correct atom. So it experiences hydrogen bonding. Where CH4 is nonpolar. So it only has London dispersion. So hydrogen bonding is much stronger than London dispersion. So the stronger IMF means it's going to have a higher boiling point. Here we have two nonpolar molecules. Two molecules that are symmetrical. So London dispersion is the strongest IMF for both of these. But when we learned about London dispersion, we talked about this really interesting idea that the larger the molecule is, the stronger the London dispersion is. So, keeping that in mind, since they're both London dispersion and we can't distinguish which one's stronger based on that, then we look at size. And the C2H6 molecule is bigger than the CH4. And because it's bigger, the London dispersion is stronger. And stronger IMF is higher boiling point. Okay, last one of these ones. Oh, C2H6. Again, it's nonpolar, so its only IMF is London dispersion. But look, we get asymmetry right here. So this is a polar molecule. So it experiences London dispersion, experiences dipole-dipole, and this one's also hydrogen bonding. Because you see how there's a hydrogen there? There's lots of hydrogens, but one of those hydrogens is bonded to either fluorine, oxygen, or nitrogen. And this one is bonded to oxygen, so it has hydrogen bonding. Hydrogen bonding is stronger, so that's going to have the higher boiling point. Okay, the last example I'm going to go through with you is extremely similar to a question on the quiz. And students tend to struggle with it because they're not thinking through the phrasing. So I'm going to have us do that together. So we have these different options. Ionic bond, dispersion, which means London dispersion, hydrogen bonding, polar covalent, dipole-dipole, and nonpolar covalent. So we have to indicate what belongs here. Okay, so indicate the bonds or intermolecular forces described. And let's do this one. Let's do strongest again. The strongest intermolecular forces described. Okay. What holds two Cl molecules? That's the big word here. Holds molecules together. So this is not saying what's holding atoms together inside of a Cl2 molecule. Here's a Cl2. It's not saying what is the intra, what's holding atoms together. Nope, it's saying what holds molecules together. So there's another Cl2. And we want to know what the IMF is that holds these guys together. So when it says holding molecules together, your choices are IMFs. So it's either going to be London dispersion, that's an IMF, or hydrogen bonding, that's an IMF, or dipole-dipole, because that's an IMF. And Cl2 is nonpolar. So the strongest IMF that it occurs between these two nonpolar molecules is London dispersion. So this one's B. Now on the next one, it says what holds atoms together. Not molecules, atoms. So instead of it being intermolecular forces, it's intramolecular forces. It's saying what is holding this hydrogen atom together with the chlorine atom? What is the bond? What is this intramolecular force, this bond. So your options are nonpolar covalent, so this is intra, so it could be nonpolar covalent, or it could be polar covalent. Okay. All right, so this bond is between two nonmetals, so it's covalent. We got to decide which one. And if you use your electronegativity table and you subtract chlorine from hydrogen, which we did earlier, we saw that it was a polar covalent bond. So this one is D. All right, here's another one that says what holds atoms together. So not molecules together, what's holding atoms together. So it's our intra. So it's either going to be polar covalent or non-polar covalent bond. What holds atoms together in a nitrogen molecule? So we got a nitrogen molecule. And what is holding these two nitrogen molecules together? Well, if you do the electronegativity, nitrogen is 3.04. But 3.04 minus 3.04 is 0. So this bond is non-polar covalent. Non-polar. Okay. The next one that it could talk about is ions. So if it's molecules, it's IMFs. So London dispersion, hydrogen bonding, or dipole-dipole. If it's holding atoms together, then it's an intra, and that's going to be non-polar covalent or polar covalent. But if it's holding ions together, then it's an ionic bond. Now, it doesn't have to say ion. You might just have to recognize that it's a metal and a nonmetal. When it's a metal and a nonmetal, then it's ionic. And so here's a good example of this. The bond that's broken when calcium chloride melts. Calcium is a metal and chlorine is a nonmetal. When it's a metal and a nonmetal, it's ionic. Those are ions. Okay. The other one that's an ion is the last one, by the way, because look, I see iron, which is a metal, and I see O2, which is a nonmetal. And so that's ionic. All right. The bonds that are broken when water boils. So that's a difficult one because you got to think about water, H2O. It's a liquid. And when it boils, it becomes H2O gas. But the important thing to note is that it's still H2O. So we got H2O, and then it warms up, it starts moving around more, but it's still H2O. So in order to go from liquid H2O to a gas that's flying around, what is overcome or broken is the IMF attraction between them. We are not breaking the bonds that hold the atoms together inside of these molecules. We're not breaking those. Okay. So what are IMFs for water molecules? We've looked at this a few times now. We know that we have London dispersion because all molecules have London dispersion, dipole-dipole because it's a polar molecule, and hydrogen bonding. And I changed this so it says the strongest. So instead of listing all three of them, I'm just going to put hydrogen bonding. We'll skip this next one, and we don't have a question similar to that one on the quiz. All right, everyone. Now, what you're going to be doing with the remaining time is you're going to be working on this review that starts on page 17 and it ends on page 20. The answer key will be at the front of the room. I want you checking your work often, but not copying off of the key. And next class when I see you, I'm going to give you 15 minutes to finish this, and then we're going to take the quiz. So take your time very serious today, and I need you to get through a good chunk of this problem set. Like, you probably want to be wrapping up at least question 13, and those are the similar ones that we just barely did together. Okay. All right, everyone, I will see you next time where we'll wrap up the review and then we'll take this quiz.